Hello, we're going to do lesson 2.11, related rates, day 1. Let's go ahead and try the warm-up. I want you to go ahead and find the implicit derivative of 1 and 2, and pause the video. When you're ready, you can go ahead and play the video and we'll go through those answers. Okay, so you've tried number 1 and 2. It's really important that we do implicit derivatives today in our warm-up because as you can see, when we do our related rates, we are going to be doing a lot of implicit derivatives today. All right, so number 1, dr d theta. So it's important to remember that r is our dependent variable. So whenever we do the derivative of r, we're going to add the dr d theta there. All right, so we have 12 theta squared. That's a theta, so no need to do any dr d theta there. Minus, we can think of this as 6r to the 1/2. So this would give us 3r to the negative 1/2 dr d theta, because we did an r. And then here we have the derivative of e, which is the same, e to the 2r. And then we have to multiply by the derivative of the exponent, which would be 2 dr d theta. All right, now we just need to isolate our variable. So we're going to bring all the dr d thetas over to the right. So there's only one thing over here. Okay, so this will be 2e to the 2r dr d theta plus 3r to the negative 1/2 dr d theta. Okay, next we're going to factor out the dr d theta. I have to take up some extra room here because I can't not write small on this. Okay, and then we're going to divide both sides by the 2e to the 2r plus 3r to the negative 1/2. All right, I'm going to erase that, so if you need to look at it longer, just go ahead and pause the video. I'm going to erase it so I can do number 2. Okay, on number 2, we have dy dx. So again, the y is our dependent variable. So every time we do a derivative of a y, we're going to be adding that dy dx on number 2. Okay, so the first one, we want to kind of think of this as sine x to the 3rd so that we can use chain rule to do that derivative. Okay, so this is 3 sine squared x times the derivative of sine x, which is cos x, plus, all right, here we have product rule, so we have a derivative of the first times the second, don't forget your dy dx, plus derivative of the second, which is 1 times the first. On the other side, we have 4y to the 3rd dy dx minus 6x. All right, I'm going to move all my dy dx's over to the left, everything else to the right. I'm going to do it all in one step. So I have 2xy dy dx minus 4y to the 3rd dy dx equals negative 6x minus y squared minus 3 sine squared x cosine x. Okay, we're going to factor out the dy dx, and we're going to divide by what is left, which is the 2xy minus 4y cubed. So this final answer would be negative 6x minus y squared minus 3 sine squared x cosine x all over 2xy minus 4y cubed. I am sure that I am making a mistake at some point in all of these notes, probably more than one. So I'm going to apologize now. If you see that there is a mistake, obviously you can't stop me and say that's a mistake. So just fix it if you are sure that I have made a mistake. All right, so today we are doing related rates. We're going to read the tips down here. Okay, let's go ahead and look at this. All right, so it says that in this section, we look at problems that ask for the rate at which some variable changes when it is known how the rate of some other related variable, or perhaps several variables, changes. The problem of finding a rate of change from other unknown rates of change is called a related rates problem. So, if you remember when we started derivatives, we would always say that the derivative is the slope of the tangent at that point. Remember that slope is the same as rate of change, okay? So if we want to see how fast something is changing, for instance, you're pouring water into a cup and you want to think about the rate at which that water is being filled in the cup, you're thinking about the rate that the volume is changing, which is the derivative of the volume, okay? All right, so let's look at the strategies here. Strategy number 1, draw a picture, name all the variables and constants. Everything when we do related rates relates back to time. Okay, so let's talk about that. Filling a cup example with your faucet. As you're filling it, how full it is depends on the time at which you are filling it. So if it's 1 second in or a minute in, it just depends. So for all of these problems, t is our independent variable. T is like our x, okay? And everything that we take the derivative of will be with respect to time. So for instance, on number 2, we did dy dx. That was derivative of y with respect to x. When we do related rates, everything is with respect to time. So the derivative of whatever with respect to time means it's all going to be dt. All right, number 2, write down the numerical information. So just writing down everything that we know, that's going to be useful. Number 3, writing down what you were being asked to find. Number 4, writing an equation that relates the variables. You may have to combine several equations to get a single equation that relates the variable whose rate you want to the variables whose rates you know. So you do have to be a little bit creative sometimes. Differentiate with respect to t, and then evaluate using known values to find the unknown rate. All right. You're going to get good at these. It just takes a little bit of practice. So the first one, we're going to get to the end and you're going to think, I never could have figured that out on my own. But you will get this. After we do a couple examples, you're going to start seeing, all right, I think I could probably do this on my own. All right, let's look at example 1. Water runs into a conical tank at the rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? All right, so let's just start by drawing a picture. This is a conical tank with a point down. Okay. All right, so it says water runs into the tank at a rate of 9 cubic feet per minute. Okay, when you are filling the tank, you are talking about the volume of the tank. So since this is the rate of the volume, this is our change in volume with respect to time. It is dv dt. All right, the tank stands point down, has a height of 10 feet. All right, so let's label that. That is 10. And it has a base radius of 5 feet. So that would be 5. Okay, remember base doesn't have to mean the bottom. It's the circular part of the cone. All right, it says, how fast is the water level rising? Okay, underline that. How fast is the water level rising? Since we are trying to find the rate at which the water is rising, we are looking for the change in the height with respect to time, dh dt. Okay, however high the water is filled, that's the height of the water at that time. Okay, so if the water level is rising, what's changing is the height of the water, dh dt. Okay, and then here it says the water is 6 feet. So what this means is they want this specific moment in time when the height of the water is 6 feet. So when the whole problem is all said and done, we're going to plug in 6 to figure out the rate of change at that particular moment in time. Okay, So the formula that we would like to use to relate all of these is the volume of a cone. If you don't know the volume of a cone, you can Google it. I happen to know it. It is V equals 1/3 pi r squared h. It's basically a cylinder, but 1/3 of that. Okay, here's the problem right now. If we were to do this derivative, we have 3 variables that are changing at the same time. So let's say I'm putting water into this. 3 things are changing: the height of the water, the volume of water, but also the radius, okay? Because if I've only filled the water up to this point, the radius at that point is not 5. It's less than 5, okay? Let me draw that a little bit better. Okay, so at any given point in time, my radius, my height, and my volume are all changing together. All right, and they relate to each other when they change. But the problem is I don't know the radius. See how they told us the h was going to be 6? I don't know the radius at the time that I want it, and I also don't know the dr dt. So there's just too many unknown variables at this point for me to do this problem. All right, so what do I have to do? I have to be creative, and I have to use what I already know to help me eliminate one of these variables, okay? And you've probably noticed they gave us the height of 10 and the radius of 5, and nowhere in this problem have we even started to use those. So I think that's going to be where we would like to create some sort of substitution so that we go down from 3 variables to 2, okay? All right, so here we have our radius to our height. The ratio of the radius to the height is 5 to 10. Okay, this means that my radius to height ratio is a half. Okay, I'm going to write that RH equals a half. So what I can do is I can multiply both sides by h, and I can say that my radius is always going to be half of my height. And what I can do now is I can actually take this. Why are you doing that? Sorry. Okay. Take my substitution and put it right here. Okay. All right. So here's my new equation. 1/3 pi half h squared h. All right, I'm just going to keep writing down this page. I'm going to ignore these other 2 problems for now because I just write way too big with my finger to try to fit all this in nicely. Hopefully you're having better luck. I'm sorry if I didn't give you enough room. All right, so what we're going to do now is let's just reduce this down a little bit, make it a little bit easier for us. We have all this multiple variables and everything, so let's just see what we got here. 1/2 squared is 1/4, h squared h. Okay, we can put the 1/4 and the 1/3 together, so 1/12 pi h cubed. All right, here we go. All right, at this point, we now are really golden because we know dv dt. We know the height's going to be 6. We're looking for dh dt, okay? So we're going to go ahead and do our derivative implicitly with respect to time, okay? So we're going to start right from the left. The derivative of v is 1 dv dt. Okay, on the right-hand side, the only variable is h. Okay, so we're bringing that 3 down in front. 3 times 1/12 is 1/4. And h cubed goes to h squared, dh dt, because we did the derivative of h. All right, at this point, we are looking for dh dt. That's what we're trying to find. We're going to plug everything else in. So we know dv dt is 9. We know h is 6. That's what they wanted us to use. And we're looking for dh dt. Okay, so 6 squared is 36. 36 divided by 4 is 9. Divide by 9 pi. So this tells me that the rate at which my height is changing is 1/pi feet per minute. Okay, and I know that's the unit because of the rate that they gave me for the volume was cubic feet per minute. So the height is changing at 1 over pi feet per minute, and that's the answer. All right, we're going to try number 2. And like I said, I'm aware that at this point you may not feel super confident, and it's going to be fine. We're going to do several examples, and you're going to start to get the hang of it here. All right, so I'm going to erase this so that I can continue with number 2. Hopefully you guys are finding a nice, neat way to make your notes, because I know mine looks horrible. You can't really copy it. All right. Okay, let's read number 2. A hot air balloon rising straight up from a level field is tracked by a rangefinder 150 meters from the liftoff point. At the moment the rangefinder's elevation angle is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, so we're going to draw a picture. We have our balloon. Okay. It is rising in the air. And we have this rangefinder over here. And they already told us it's 150 meters away. It forms an angle. I don't want to put my 150 there, do I? Put it down here. It forms an angle with the balloon, okay? So notice here, it says, we already labeled the 150. It says, at the moment the rangefinder's elevation angle is pi over 4. Okay, so they're telling us the moment that they want us to evaluate this. The theta, they want us to evaluate it at pi over 4. Then it says the angle is increasing at the rate of 0.14 radians per minute. That is the rate at which theta is changing. So it is our d theta dt. Okay. And they want us to see how fast is the balloon rising. Okay, so that's going to be our height over here. I'm going to call that h. That's the height of the balloon. Since they want us to see how fast it is rising, that's our dh dt. That is what we are looking for on this one, okay? All right, so now we want to kind of take a step back, look at everything that we have, look at the situation that we have on this triangle, and let's try to think of either a formula or a equation that relates all of this information to each other, the height, the theta, and the 150 that we have. Okay, so hopefully your mind is going to tangent, because here we have an angle, here we have the opposite side, h, and the adjacent side, 150. Okay, so we're going to do tangent. Tangent of theta is equal to opposite over adjacent, h over 150. All right, so at this point, we are going to take our derivative from left to right, starting with tangent. Tangent of theta, that's going to be secant squared of theta, d theta dt, because we did the derivative of theta. On the other side, our variable is h. Okay, so you can think of this as a 1 over 150h. So when I do the derivative, I just get 1 over 150. dh dt, because I did the derivative of h. All right, now I'm plugging everything in. So my theta is pi over 4. My d theta dt is 0.14. And I'm looking for my dh dt. All right, secant squared of pi over 4. Remember your t-chart? At pi over 4, the point is radical 2 over 2, radical 2 over 2. Okay, since it's secant, it's cosine, but the reciprocal. So it's going to be 2 over radical 2 squared. All right, when I square that, I get 4 over 2, which is 2. That gives me 0.28. I need to multiply both sides by 150. I'm running out of room, so you guys are gonna have to forgive me. I'm skipping some steps here. And when I do 2 times 0.14 times 150, I get 140. Feet per minute. Okay, sorry, it's actually 42. I don't know why I thought it was 140. I had that written down. I must have had a mistake there. 42. I was just thinking that seems a little high. 0.28 times 150. Okay, 42 feet per minute. That is correct. All right, I'm gonna erase this, so go ahead and pause it if you need it longer, and we'll try number 3. Okay, number 3. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? All right, so first we're going to draw a picture. Okay, we have this police cruiser. I'll just put a dot here. It's coming this way. And then we have this other car is going east. And the police cruiser is chasing this car. All right, so let's go through each thing. So it says the cruiser is 0.6 north. So that's going to be this distance right here is 0.6. In fact, you know what? Let's label this X and Y. Okay, so we know that at this moment, X is 0.6. At the particular moment T that they want us to evaluate. The car is 0.8 miles to the east, so our Y is going to be 0.8 when we evaluate it. And then it says the police determine with radar that the distance between them and the car, so that's this, and we'll call it Z. So the rate at which their car is getting further away is 20 miles per hour. So that's our dz dt. The rate at which Z is changing is 20. And then it says the cruiser is moving at 60 miles an hour. So that's dx dt is going to be 60. Now we have to be careful here because since x is going down, it's actually going to be negative 60. Okay, so remember, velocity can be positive or negative depending on if you're going forward or backward. So since this is kind of like an XY plane, since x is going down, it's going to be negative. And we want to know the speed of the car. So the speed of the car is going to be our dy dt. That's what we're looking for. Okay. All right, so if you're looking at this triangle that we've drawn with x, y, and z, you should be kind of coming up with the relationship between this being x squared plus y squared equals z squared, Pythagorean theorem. All right, so now we're going to do our derivative. So we get 2x dx dt. Remember, everything is in relation to time, so we need everything gets a dx dt or a dy dt or whatnot. Plus 2y dy dt, and then 2z dz dt. Okay, so at this point, since we're looking for dy dt, we want to have something to plug in for every other variable here, okay? So we already know our dx dt, we know our dz dt, we know our x and our y, so the only thing that we don't have is our z, and we're just going to use Pythagorean theorem for that. So we're going to do x squared plus y squared equals z squared. We're going to plug in our x, 0.6, plug in our y, 0.8, so that's 0.36 plus 0.64, which is 1. Okay, so now we're going to plug everything in. So we have 2 times 0.6 times negative 60 plus 2 times 0.8 times dy dt equals 2 times 1 times 20. So I'm running out of room, so I'm just going to write 40. Okay. All right, so if we do 2 times 0.6 times negative 60, that gives us negative 72 plus 1.6 dy dt equals 40. Add the 72. Divide by 1.6. So the car is going 70 miles per hour. All right, so you guys are going to try your homework. Your homework has the first page. These are very simple. So it's really just letting you do the actual algebra, doing the implicit derivative, plugging everything in, okay? Number 1, you're doing the implicit derivative, and then you are solving for ds dt, okay? On the back, I gave you one problem that's actually like the notes in terms of setting up the whole problem, solving it, and finding the answer, okay? I really want you to give it a good go. I don't expect you to read the problem and go, okay, I know exactly what I need to do. Like, just start. Start by labeling all of your variables. Start by writing down anything that you do know that is changing, like a dx dt or a dy dt or something like that, okay? And just really give it a good shot. And I'll conference with you guys any questions that you might have. All right, good luck.